Okay, let's first review a little bit. Z-scores from chapter 4, section 1. Remember, the Z-score was X minus X bar over S. And what it tells us, the Z-score tells us the number of standard deviations our X is from the mean, X bar. So the formula is Z equals X minus X bar over S. So let's pretend our mean was 50 and our standard deviation was 10. If we drew the bell curve, okay, remember, it has to be normally distributed, which means it has to be a bell curve. Normally distributed means bell curve, which means that from the mean, 50% of the data is to the left of it and 50% is to the right of it. That's what normally distributed, that's why you use a bell curve. So if our mean was 50 and each standard deviation was 10, so we add 10 to 50, we get 60. Add 10 to that, we get 70 and 80. So that's one standard deviation is 60, two standard deviations is 70, and three standard deviations is 80. To the right. And going back to the left, we subtract our standard deviations. So 50 minus 10 is 40. That's -1 standard deviation. 40 minus 10 is 30. That's -2 standard deviations. And 30 minus 10 is 20. That's -1 standard deviation, or -3 standard deviations, I'm sorry. So far, so good. So that just says from the mean, we add 10 each standard deviation, and then we subtract 10 standard deviations as we go to the left. Because it was normally distributed, remember we have the 68, 95, and the 99%, 99.7% rule. Within one standard deviation from the mean, both sides, we have 68% of our data. Within two standard deviations, we have 95% of our data. And then within three standard deviations, that's 99.7% of all our data. That's perfect. If it was inside those, we can figure out what each one of those areas consist of. So since one standard deviation both sides is 68%, that means there's 34% to both sides of the mean, to one standard deviation. Because 34% is 68%. Okay, now in the second standard deviation, we know it's 95%. So 95 minus 68 is 27. So we know inside these small areas that constitute inside the second standard deviation, the total is 27%. So if we divide it by 2, we get 13.5% in each of those sections. Good question. The percentages come from trial and error, not trial and error, but a whole bunch of errors with more and more sample sizes. As you get it, and if it's normally distributed, that means it's a bell curve. That means the middle of the data is also the mean. So, and because of that, we can determine mathematically that within the first standard deviation, that's 68% of our data. So what we would have done is we have all our data and we count all the numbers from 40 to 60. That's one standard deviation from the mean, from 50. And what we'd come up with is 68% of the, so if we had a number, 100 numbers, 68 of them would be within that first set. And then after that, from the first standard deviation to the second standard deviation on both sides, we'd get 30, on the average 13.5% of the data of numbers. And then lastly, in the 99.7%, so if we take 99.7 and subtract 95, we get 4.7%. Divide that by 2, we get 2.35% of our data falls in that small little area of the third standard deviation. Which means now we have the tails, the very far ends. Since everything in the 3 standard deviations is 99.7, that leaves 0.3% left. If we divide 0.3 by 2, we get 0.15%. So that's how much is in the small little tails at the end, 0.15%. Always when we come and check the table. All right, so this works great. If I said, okay, now we have this. If I said, what percent of the data is below 70? Remember, 70 is 2 standard deviations to the right of the mean. So that is 34% for the first standard deviation, 13.5% for the second standard deviation, which makes it to 70. And then we have the 50% that's below 50. Remember, half of the standard deviation, half of it is to the left of the mean, half it's to the right. And so for the 70, all we have to look at the first 2 deviations to the right, because we know everything to the left of it is 50%. So what we're going to have is 97.5% is below 70 by adding up the 50%, the 34%, and 13.5%. So it works great if it falls on the standard deviations. And the standard deviations are 60, 70, 80, 20, 30, 40. What if I wanted to know what percent of the data is below 45? Forty-five is within that first standard deviation to the left. The mean is 50. The first standard deviation to the left is 40. So 45 is between there. That's our X value. We know that the mean is 50 and the standard deviation is 10. So we plug it in our Z formula. X minus X bar over S. 45 minus 50 over 10. 45 minus 50 is -5 because 50 is bigger than 45 and it's negative. 5 divided by 10 is 1/2, which is 0.5.
Excuse me, sir. I have a question.
Yes.
Oh, in the first one below 70, why did you add 50%? Because we already calculated
No,
percentage for
because I
each
had 50%, because if you look at the bell curve, the mean is at 50.
Mhm.
So we know that there's 50% of it to the left.
Yes.
Then we have the first standard deviation to the right of it, which is 34%.
Mm-hmm.
And then the second standard deviation is 13.5.
Yes.
So everything below 70 is the sum of those three numbers. That makes
Okay.
sense?
Okay, okay. The 34% and 13.5 is to the right.
Yes.
Why the whole of 50 on the left is below 50?
Everything below 50 constitutes 50% of my data.
Okay.
Everything to the right of the mean constitutes 50% of my data.
Okay.
So everything below 70, I have to add up all three of those numbers, the
Okay.
13.5, 34, and then 50.
Thank you.
You're welcome. You're welcome. So before 45, so we have 45 minus 50 is -5 over 10, which is -1/2, which is 0.5. So now what we have to look at here is this number is our z-score. Our z-score is -0.5000. What we have to look at here is these numbers inside here are our z-score numbers, the numbers inside the table that tells us the percent. So at 0.5, it's -0.5. So we come over here. On the left-hand column is the first decimal to both sides of the decimal, -0.5. The first column is zeros, second column is the 1. So it's this first column location here is 0.500. The second column at 0.01, that one is 0.51, 0.52, 0.53. These numbers inside here tell me the percent of the data. So it's 0.50. So I use this number, which is 0.3085. Make it into decimals, that's 30.85% of the data are below that number. So that's how the z-score chart works. You do the z-score calculation, find the first decimal on both sides of the decimal on the left column, and along the top is the second decimal. And then you see where they intersect, and that tells you how much percent of the data is to the left of that number. So if we had, let's say, if we had 0.069% was to the left, how much of the data would be to the right of it? If our z-score was, what was that again? If it was -2.46, we go to -2.4, go all the way down to a CS6, which is that column, and we get this 0.0069. 0.0069. convert that to percent, we get 0.69%. Remember, this number is everything to the left of that. So how much of it is to the right of it?
To be 0.3 points. No,
How many percent is in the whole thing?
100%.
100%. And if 0.69 was taken away,
That would be 99, no,
99.31%.
90.331.
Exactly, yes. Then we'd have 99.31%. That's called, which we're going to talk about in this next section, that's called the complement. Since we were given this information to the left of that z-score, to find everything else, we take 100% and subtract what our z-score was. And that will give us our remainder of the area.
Smith, sir, how do we know the column? How do we know the column to check for the
Your z-scores are always going to be 2 decimal places.
2 decimal places?
Yes.
Like in the first one, with that, where we had minus 0.5, we took the first one.
Well, yeah, because it was minus 0.5. That means the next decimal, the second decimal is 0.
Okay. And this one, minus 2.4.
But
We went all the way
so
to
we went to
0.6.
negative 0.5. And these numbers up here on this on the top row gives us a second decimal location.
Okay.
This one is a 0. This one's a 1. So at negative 0.5, 0.
Okay.
Negative 0.51. Negative 0.52. So that's how that reads. These numbers on the top of the columns represent the second decimal place. Each of these numbers, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Those are the second decimal places. The first decimal place on both sides is here on the left, the entire column. What you have to do is now find out where they match.
Okay, we pick 0.06 with 2.4. What my question is, why didn't you pick the first or second one? Why did you pick the sixth one?
Okay, I had to start with some examples somewhere. I have to give a number to show you how this thing works.
Okay.
And you could do it 2 ways. You could do the calculation of the z-score with that formula, x minus x bar divided by s. Or if I give you the z-score, you look at the percent. Or if you want to know the percent, you can calculate the z-score. So again, the z-score itself, you calculate it using that formula, z equals x minus x bar over s. That'll give you the first decimal place on this far left column, the second decimal place along the top. And then where they correspond, where they intercept, that is the percentage of numbers to the left of that z-score. You get your z-score. To the left of it, that's the area. So to calculate everything on the other side, subtract it from 1. All right, so that's what I wanted to go over. We'll do more of that stuff when we do hypothesis testing. So now, section 2 deals with addition and multiplication of percents. So let's look at the addition rule of percents. We know we're using addition whenever you, in the question, you use the word or. The word or, because if you're adding two numbers, it could be this one or it could be that one. When you're multiplying them, you'll use the word and. Because it has to be in this one and it has to be in this one. So the probabilities have to be multiplied. So we're at probability of A or B. Remember, A or B are the events. So it's P, parenthesis, A or B, close parenthesis. What that means, it equals the probability of A plus the probability of B. Now you gotta think about this. Why is it addition? Why is or connected to addition? Because if we had two events, and I said, okay, what's the problem? Everybody familiar with a deck of cards? A deck of cards has 52 cards in it. They're separated into four suits. You have the diamonds, you have the hearts, you have the spade, and then you have the club. The diamond and the hearts are red cards. The spade and the clubs are black cards. Each set starts off at the number 2 and increases all the way to 10. Then it has face cards. The jack, the queen, the king, and the ace. So if you count those, we have a total of 13 cards. So there's 13 cards in each suit. There's 13 diamonds, 13 hearts, 13 clubs, 13 spades. So 4 times 13 equals 52 cards. So now my probability, what's the probability of getting a red card? Remember, the formula for probability is the number of outcomes desired divided by total number of outcomes possible. So it's part over total. So our question, probability of a red card. How many red cards are there?
26.
There's 26, yes, because there are 26 diamonds, 13 diamonds, 13 hearts. There's 26. And how many cards? 52. So 26 divided by 52 is 1/2. Or if you wanted to, you can go further. 1/2 is 0.5 times 100, you get 50%. So the probability of picking a red card is 50%. Or if you let it as a fraction, that's even more indicative. What it says is, for every 2 times I pick a card, I will get at least 1 red card. That's why fractions are a lot more exact than decimals and percentages. Okay, how about if I pick a red 10? So how many red 10s are there? There's two, because we only have two red suits, the diamonds and the hearts. And they go from 2 to 10. So we have two red 10s out of 52. So 2 divided by 52. That simplifies into 1/26. Okay, how about now if I get a king of hearts or a 3 of clubs? What is that probability? A king of hearts or a 3 of clubs? So we look at both of them separately. The probability of king of hearts plus the probability of a 3 of clubs. So what's the probability of getting a king of hearts? What's that? 1? No, 1's 100%. I mean, just gets it all the time. What's the probability of king of hearts? How many king of hearts are there? How many cards are there? So it's 1 out of 52. Has to be a fraction. Because every probability is between 0 and 1. You can't get higher than 1. How about a 3 of clubs? 1/52. Very good. 1/52 plus 1/52 is 2/52, which is 52, which is 1/26. Which tells me this. If I picked 26 cards out of the deck and put it back and pick one, look at it, put it back, I will get at least one king of hearts or 3 of clubs. I get it one time if I did it 26 times. Now, if all of us had a deck of cards and we picked a card, looked at it, put it back, picked it, looked at it, put it back, would we all get one out of 26 tries, one of those king of hearts or 3 of clubs? No. One of us can get 4 of them. The rest of us get nothing. It just says that in the long run, in the what's called the law of large numbers, just because it doesn't work the first time, you did 26 cards and you didn't get a king of hearts or a 3 of clubs, doesn't mean that that's a false claim. It simply means you have to do it more and more. On the average, that's what this 1/26 means, is on the average, if you pick 26 cards out of a deck, one of them will be a king of hearts or a 3 of clubs. It doesn't mean it's always going to work. It just means that there's a large probability that this is going to happen. Same thing if we each had one die. How many sides are there on a die? It's a cube. How many sides on a cube? 6. And each side is made up of a number. 1, 2, 3, 4, 5, 6. So these are your outcomes. 1, 2, 3, 4, 5, 6. What's the probability of rolling a 3? 1 out of 6. Yeah. Now, what does that tell us? What does 1/6 tell us? Yeah. You'll get 3 one time if you roll it 6 times. Okay, you roll it 6 times, you got no 3s. You roll it 6 times, nothing again. Roll it again, you get 4 3s. It just says again, it doesn't say it's going to happen all the time. It just says it's going to happen eventually. With the more times you try it, it's going to happen. That's what the law of large numbers is all about. What if I said, I want the probability of a 3 or the probability of a red card? So it's a probability of a 3 plus the probability of a red card. Oh, sorry. Well, the red cards, we're done cards. Oh, yeah, we'll do that when we do multiplications. We're switching them. I'm sorry, yeah, I should have said I'm switching. What's the probability of getting a 3 from a deck of cards? Exactly 4 out of 52. Because there's a 3 of hearts, 3 of diamonds, 3 of spades, and a 3 of clubs. How many red cards are there? There's 26. The red cards are the hearts and the diamonds. Adding fractions, if you have the same number on the bottom, just worry about the top. So we're saying our chances are 30 out of 52. It would seem so, but no. Are there any overlapping cards? Which ones? Exactly. Because the 3s that we picked, 2 of them are red. So they're in here also. Right. What we have to do is we have to discard where they overlap. Okay, that now introduces the difference between independent and dependent. And then joint and disjoint. Independent events do not affect other outcomes. Dependent events do affect other outcomes. Here's an example. We have a deck of cards. If I take a card out and look at it and keep it, will that change the probability of the next card? Why? What's that? Exactly. Because if I took the card and kept it, I don't have 52 cards anymore. I only have 51 now. So it changes the probability. That's independent dependent. Joint and disjoint. Disjoint means that 2 events cannot occur at the same time. Two events cannot happen at the same time. They are what we call mutually exclusive. And joined means that they can happen at the same time. Which that's a whole nother story. So in our example we just had, the probability of a 3 or a red card, those are dependent events because we can have two things happening at the same time. They are not disjoint. So our formula now changes. The probability of A or B, the events A or B occurring, is the probability of A plus the probability of B minus the probability that A and B occur at the same time. So the probability of A or B, the probability of A occurring plus the probability of B occurring minus them both occurring at the same time. So the probability of getting a 3 plus the probability of getting a red card minus the probability of getting a 3 red, or I should say a red 3. So that's the true formula for addition. Because we have 4 out of 52 cards that are 3s. We have 26 of them that are red out of 52. And there are 2 red 3s in that deck. So we have 4 plus 26 minus 2 is 28 over 52. So whenever you're asked to if the word or fits inside there in the question, the probability of this or this, then you have to make sure that you have to ask yourself, do they occur at the same time? Like probability of rolling a 3 with 1 dice or getting a red 3 from a deck of cards. Can those two events happen at the same time? Let's look at these. So the first one is the probability of rolling a 3 plus the probability of getting a red 3 minus the probability of rolling a red 3. So obviously, rolling has to do with the die, right? So what's the probability of getting a 3? 1 out of 6. The second one has to do with cards. The probability of getting a red 3. 52. Now, the next one is minus the probability of rolling a red 3. So it's 0 over 52. I'm glad you said that's not possible, because in probabilities, we'll talk about that in a second, it goes between 0 and 1. So 0 divided by 52 is 0. So now we have 1/6. We can simplify this. Plus 1/26. You use the butterfly method. 1 times 26 is 26. Plus 1 times 6 is 6. That goes on top. On the bottom, it's 6 times 26. It's 156. So 26 plus 6 is 32 over 156. That's the probability of rolling a 3 and pulling a red 3 from a deck of cards. Remember, the probabilities are between 0 and 1. Is it possible to get a 0? Yeah, we just did it. If I have
Yes.
if I have a bag full of coins, can you pull a $5 bill out of there? No, because your bag is only full of coins. So there is no $5 bill in there. So that's a 0. This is impossible. It'll never occur. And the other end is 1. 1 equates to 100%. It's 1 in decimal. 1.0. Which is, it will occur. Anything else has to be between there. So whenever you hear people say, I will give you 120% of my effort. Is that possible? No, because if you give me everything you have, you give me 100% of yourself.
100%, yeah.
You can't give me 20% more because there is no such thing as 20% more of 100%. So everything has to be between 0.0 and 1.0. And the summation of all your probabilities has to equal 1.0 or 100%. If you take all the probabilities and add them together, then they have to equal 100%. Let's prove that. We're looking at one die being rolled. So we have the outcome on top and the probability on the bottom. So what are my possible outcomes? I can roll a 1.
1, 2,
3,
3, 4, 5,
4.
6.
Right. And what's the probability of rolling a 1?
1.
1
time
over 6. Rolling probability of rolling a 2?
1 over
1 out of
6.
6. And then same for
1
all
over
of them, 1 out of 6. If I add up all my probabilities, 1 6 plus 1 6 plus 1 6 plus 1 6, they all have a 6 on the bottom, so I just add the tops. And there are 6 of them. 1 plus 1 plus 1 is 1. 6 over 6 is 1. If your probability does not equal 1 when you add them all together, you did something wrong. Go back, look at it again. These are always checks and balances that it does here. Let's take another example of using words. Here is our example. Oops, that's too big. So it says this. 555 people were sampled. And of that group, there were 50 of them who admitted to using drugs. And 505 who said that they did not use drugs. Of the subjects showing admitting to using drugs, 5 were tested as they did not use drugs. That's called a false negative. A false negative is it's supposed to be positive, but it came out negative. Of the 505 who said that they did not use drugs, 25 of them tested positive, even though they didn't use drugs. That's called a false positive. Find the probability of selecting a subject who had a positive test results or used drugs. So with this information, how do we figure it out? We know that there's 555 total. So that's my N. That's my denominator. Find the probability of selecting a subject, a person who had a positive test result or used drugs. So by looking at this, let's make a chart of this. We have positive that said yes. And then negative, they said no. Well, let's hold on real quick. We have to break down the possibilities. Then they say the next, we have the columns. They use drugs, do not use drugs. Because remember, in our information, there were 50 people who admitted using drugs, and 505 said they did not use drugs. Of the 50 that said they did use drugs, 5 of them were tested as negatives. Of the 505 who said they didn't use drugs, 25 said they did, which was a false positive. So, how many people used the drugs and came out yes? 45. There were 45 of them.
45.
How many of them used the drugs that came out no?
5.
5. This was the false negatives. These are the true positives. Now, how many people said they didn't use drugs and came out to be positive?
Please consider.
25. That's your false positive. And so how many of them didn't use drugs that came out to be negative?
Do not use drug.
480. How'd you get 480?
505 minus 25.
505 minus 25. Very good. So with this information, we have to come up with, find the probability of selecting a subject who had a positive test result or uses drugs. Positive test result or uses drugs. So the first one should be pretty easy. Positive test results. How many of them were there?
45.
No, for the positives right here, the first row, we had 45 plus 25, which was exactly 70.
17.
How many people said they used drugs? There's 50. So, and remember, in a total, we had 555 people. So if you notice this, the positives, there were 70, the users were 50, they overlap right here. So what we do is we'll take this 70 and these 5, we got a total of 75 over 555. That's the probability of getting a positive test result or the person uses drugs. Because what we could done, we can take these 70 plus these 50 and subtract where they overlap, which will give us 75. So that's how we have to treat the data whenever we have overlapping data.
So what did you add to 70 to get 555?
Well, first off, 555 was all the
The
data put
total,
together.
yeah.
So if you add up all the data put together, we get 555. Because if we took 480 plus 5, we got 485. 485 plus 70 is 555. Then look at the columns. 45 plus 5 is 50. 25 plus 80 is 505. Add those together, you get 555. So that's how we build a chart like this. So if 75 out of 555 tested positive or used drugs, what's the probability of getting a negative test result or did not use drugs? If 75 over 55 was positive test results or uses drugs, what's negative test results or didn't use drugs?
$480.
Why is it 480?
555 minus 75.
Okay, so let's look at our table now. Didn't use drugs was 485. I mean, no test results was 485. Did not use drugs was 505. And they overlap at 480. So 505 minus 480 is 25 plus 485 is 510. Because we have a lot of overlapping data here. Doesn't mean it's the exact opposite. So it's 510 divided by 555. That's the probability. Complementary events are denoted as the event with a bar over it. Like, for example, a bar. of A bar over it. Because earlier we said the probability of A, let's say, equals 30%. Actually, I can't use percent. It would have to be 0.3. The probability of A is 0.3. So what's the probability of what this is red is not A? So the probability of not A would be what? 0.70. Because remember, the sum of all your probabilities has to equal 1. There's only, yes. It'd be just 0.7. Because we have, if we add 0.3 for A happening, then we have to add 0.7 of A not happening. So that equals 0.3 plus 0.7 is 1.0. So the summation of all your probabilities is 1, which is the probability of A plus the probability of not A. So with that, we can figure out, since we know that 1 equals probability of A plus probability of not A, then if we just know that information, to find the probability of A, we can take 1 minus the probability of not A. Or conversely, just subtract what you know from 1 and you get the other one. Example 3. Based on a survey results of customer technology associates, the probability of randomly selecting a household of the United States and getting one with a smartphone is 0.87. Family with a smartphone. What's the probability of picking a family that doesn't have a smartphone? Wait, what, 15? 13, yes. The probability of not getting a family with a smartphone is 0.13. Very good. Because it's 1 minus 0.87. So that's addition and subtraction. What word tells you in the question if it's addition? Or. So addition equals or. Multiplication deals with the word and. The probability of A and B occurring. Remember, in the addition, in the or statement, all you have to do is one event, and that's an or. So it's either going to be this one or it's going to be this one. For and, we have to do multiple events. Basically, what you're looking at here is the probability of A occurring times the probability of B occurring. That's not correct, but that's in a nutshell what we're trying to do. We have to look at both of those. So, for example, probability of rolling a 3 and picking a 3 from a deck of cards. So the probability of rolling a 3 times the probability of picking a 3. What's the probability of rolling a 3? 1 out of 6.
1 over
Probability of
6.
picking a 3?
1
Four
4
over
over
Right. So we simplify the 4 over 52 is 1 over 13. 1 times 1 is 1. 6 times 13. So it's 1 over 78.
Sorry, why 4 over 52?
What's that?
Why do you have 4 over 52 in picking a 3?
Because in a deck of cards, how many 3s do you have? In a deck of cards, there are 4 3s. 2 reds and 2 blacks. And there are 52
Okay.
cards.
Okay. All right.
And I'll send everybody also the printout of all the cards in a deck of cards, because a lot of people are not familiar with the standard deck of cards. So don't feel bad at all. So that means you could try it 78 times. And out of those 78 times, it may happen 1 time. That's a lot. A lot of tries. Now, let me show you the formula we're looking at, because now we have to introduce this statement here. What this says, it says it's the probability that B occurs after, or if A occurs first. That's what that tells us. Well, it kind of makes sense. Because if A doesn't occur, it doesn't matter what B is, because it's an and statement. They both have to happen. They both have to be true. So you're just looking at what the probability of B is of occurring. This is where independence is important. Independent events. Remember what independent was? One event does not affect
The other.
the other event. Here's an example. The deck of cards. The probability of picking a red 3 and a black 10. What's the probability of picking a red 3 and a black 10? Well, actually, we can't answer that question just yet. What's missing? We have to determine first, is it with or without replacement? In other words, when we pick the first card, do we keep it or we put it back? So we have to know that first. Whenever we do when we do multiple events, we have to determine, are we dealing with replacement or without replacement? Let's see what happens if we do them both. So the first one we'll do with replacement. And the next one we'll do without. So with replacement, what's the probability of rolling a 3 or picking a 3? 4 out of 52. Now that 3 occurred. So now what's the probability of the second time rolling it, picking a 10? Black 10. Yes. Very good. 2 out of 52. Oops, the first one's 2 out of 52 also. Because there's only 2 red 3s and 2 black 10s. So we simplify both of them, 126 times 126, which is 1 over 26 times 26. Now let's look at without replacements, the probability of a red 3. There are 2 red 3s out of 52, and we keep it. It's without replacement. So how many black 10s are there? 2, 1. Because we kept one of the cards. So it's 2 over 51 now. So we can simplify that to 1 over 26 times 2 over 51. So you see, it changes the odds dramatically. It depends, it changes what the outcome is going to happen dramatically. So you have to be cautious about, can the events happen at the same time? Can they overlap? Are they independent or are they dependent? Example 4. Drug screening and the basic multiplication rule. Let's only use the 50 test results of the subjects who used drugs. Remember, we had out of the positive test results, we had 45. Of the negative test results that tested positive, we had 5. So we had 50 people who were positive for the test results. So let's look what this is going to be asking. If 2 of the 50 subjects who used drugs were randomly selected with replacement, find the probability that the first selected person had a positive test result and the second selected person had a negative test results. The probability of a positive result. Of a positive result. And the second will be a negative result. This is with replacement. So what's the probability of getting a positive test result? Remember, of our chart on top, we have positive test equals 45, negative test is 5, so the total is 50. 45 over 50 times possible probability of a negative test result. 5 over 50, right? So we could simplify those, 1 over 10. So we got 45 over 100. You can simplify that. 5, 3.
So you said 45 over 100. 50 times 10 is 500.
500, yeah. So they go in there 0.05 goes in there 9 times. So it's 9 with 2 zeros, 0.09, which is 9%. That's if the first person selected was a positive result, then the second one was a negative result. Now, this is part A. Now, repeat that same experiment, assuming the two subjects were selected without replacement. Very good. And 5/49. So we have 45/490. This was 45/500. This is 45/490. That one's gonna be 0.901 or 2. So yeah, even though it's to the third decimal, this one is 9.1% chance of occurring. Okay, let's see which will be drug screening and the 5% guideline for cumbersome calculations. That. Birthdays. Example 6. When two different people are randomly selected from those in your class or friend group, find the indicated probability by assuming that your birthdays occur on the same day of the week with equal frequencies. 1. Find the probability that the two people are born on the same day of the week. So in other words, the first person, let's call him A and B. So if they're both born on the same day of the week, what's the probability there? 1 out of 7. Only 7 days, right?
Mhm.
Find the probability that the two people are both born on Monday. A on Monday and B on Monday. So the probability of A on Monday is 1/7. And the probability of B on Monday is also 1/7, which is 1/49. Ooh, significance. So that's just looking at, okay, whether it's one day of the week or if both people are on the same day of the week. So it's the way the sentence is stated that how you interpret what it's asking. Example 7, using probability for significance. What is significance? Significance is, it tells how many decimal points are we going to be accurate to. It's a level of significance. Because as you saw the last one, the first one was 0.09, the second one was 0.091. So at 2 decimal places, they're both equal. But at 3 decimal places, this one's more significant because it's higher than this one. The 0.091 is higher than 0.090. It's more significant. So what it says here in this question, let's now revisit the chapter problem and apply what we have learned about independence and multiplication rule. The chapter problem describes how the XORT method of gender selection was developed to help couples have baby girls when they have children. If a test of the XORT method of gender selection involves 20 couples, so N equals 20, who give birth to 20 babies, what is the probability that the 20 babies are all girls? Does the result of 20 girls suggest that the XORT method is effective? So basically what's asking is, what is the probability that 20 babies are born and they're all girls? So how do we calculate this? "20 babies and girl." So what we're looking for is, what's the probability of getting a girl as a birth? What are your chances?
1/20.
1/2 of getting a girl. If the baby's born and it's a girl, you get a 1/2 chance. Now this happens 20 times. This was the first event. The next one was 1/2. The next one was 1/2. We do this 20 times, what we end up with is that probability. The probability that all 20 are girls. So 0.5 to the 20th power. Because remember, why is it multiplied? This is what you have to in your head. Think of the events. You have 20 babies being born. The first one's a girl. The second's a girl. The third's a girl. Keep on going, and do you use the word and or in this statement? You have to use and, because if the first one's a girl and the second's a girl and the third and the fourth, so that's why you're multiplying them. That's why it becomes 1/2 to the 20th power. Redundancy. What is redundancy? What does it mean? Have you ever heard the word redundancy? To repeat. For example, in computer systems, if you have a redundant system, that means it's going on, you have multiple systems going at the same time. For example, at the airport, they used to have them where they were in series. If one crashed, then they go on to the next one. But the problem with that is not all information was carried forward. Or if it was carried forward, it could have been corrupted when the first system crashed. So we went in series, where instead of going from computer system A to computer system B to computer system C, ours
Excuse me,
went like
Professor.
this.
Excuse me, sir. The
Yes.
second question was not treated. Does the result of 20 girls suggest that the XORT technique is effective?
Let me see what it asked. So does the result of the 20 girls suggest that the XORT method is effective? So can you tell me anything about the result being predictable? No, but I mean, it's all born by chance. The system's not doing anything because you get a 50% chance each try.
Okay.
So the XORT method doesn't do anything. It doesn't predict one way or the other.
Okay.
Thank you for that.
Yes, sir.
So redundancy is where you have more systems backing up to make sure it works together. Example 8. The Seagate hard drive model ST4000DM000 had a failure rate of 2.89% in a year. If your computer has only the Seagate hard drive model ST, what is the probability that it will work for a year? The probability will work for a year. All we know is the failure rate for a year is 2.89%. If it's 2.89% to fail, what is it to pass? Yeah, take 100% minus 2.89. So it's 97.21%. Right, so all we do is take our 2.89 and subtract it from 100%. And we get our answer. If your computer has two Seagate models hard drives, what is the probability at least one of them will work throughout the year? So if we had two of them, the probability of the first one failing was 2.89, and the probability of the second one failing, 2.89. Multiply those together, that's the probability of both of them failing. So we take that number, subtract it from 1, or 100, because these are percents. 2.89 times 2.89. And that'll give you the probability that at least one of them will work. So this is going to be pretty close to 99.9% chance that's going to still work. Another way we can represent our outcomes, because these are just numbers of probabilities. How can we visually see what outcomes are possible? Let's look at this one example here in the rationale. We have a pop quiz. Two questions. The first question is a true or false question. And the second is a multiple choice question. So the true and false question was, a pound of feathers is heavier than a pound of gold. True or false?
Come again, please.
What's that? True or false?
Can you repeat that question again?
Yeah. A pound of feathers is heavier than a pound of gold.
False.
False, because a pound's a pound. And the multiple choice was by a small sample, we may judge of the whole piece from a small sample. And we had A, B, C, D, E. Those are all possibilities. So we had this. How many possible outcomes are there? Because remember, to find the probability, we have to know the total number of outcomes. How many outcomes are possible in the first one? 2, either true or false. How many in the second?
5.
2 times 5 is 10. So there's 10 possibilities. So let's look at this graphically. Our first event is either true or false. It's either going to be true or it's going to be false. Now, if the person picked true, then they can pick one of these 5. So from here, we can pick A, B, C, D, or E. And if they pick false, then the second one, they can pick A, B, C, D, E. So these are all of our possible outcomes. They pick true then A, true then B, true C, true D, true E, false A, false B, false C, and false E. So the probability of getting it correct would be what? Probability of making 100 is what in this test? How many right answers are there? I mean, 2. These are the answers. How many right answers are there? There's 2 parts. There's only one. The right answers is going to be true A, true B, or whatever. There's only one of those. There are 2 parts. There are 2 questions, but there's only one of them that's correct. Out of how many? So that's the probability of making 100. You look at these are the outcomes. These are your solutions, not these. Let's say it's this one. This is the correct one. Everything else is wrong. I know you're thinking there's one here and then there. No, but this is the quiz. These are the answers. What do you think? Do we have time to do the next one? Yes.
Yes.
2. Didn't I give you those last week? Oh, you okay? I have a bunch of these extra ones. Okay, so that's section 2. And we only have half an hour left.